Okay, hello everybody. Today I'm going to discuss the general architecture of a data layer, data ecosystem, whatever you want to call it, starting from ingestion all the way to visualization, including all of its component parts and high-level architecture. At the end of this, you should be able to understand the general architecture of how any data ecosystem on the planet works. I'm going to try to avoid some of the rabbit holes and details that there might be associated with some of these areas, but that's beyond the point. So that's what we're going to talk about today. So let's kind of just get into it. The core of any data ecosystem is always going to start with your ingestion layer. That's where you get your data. That's always going to be your most important part. Since we're talking about generics here, I'll give kind of some high-level ideas of where data could come from. But there's so many places that this data could come from, depending on your company and how and your ecosystem, that it's impossible to be fully accurate in it. So obviously, if you're just like a generic tech company, you're going to have your microservices that produce data. And so this data is going to come in some sort of format. Likely, you will have some sort of like library here that has this data. And there are potentially many ways of discussing this. We'll discuss this in a second. But what will likely happen is you're going to want to take this data and you're going to go into some sort of collector. And so the library will go to a collector. And this collector will be some form of API connection that does this. It could be REST. It could be gRPC. It could be any form of connection like that. It could even be like a custom protocol. But that connection will likely happen to an API of some sort. And then this API will deliver that data. And there's a few things that can happen here, but the most common options here are that it's going to go towards and into a streaming layer. And so this is going to be something like Kafka, Pulsar, something like that. And we won't talk about the details of what happens in there, but then that data will eventually land in S3 through a job of some sort. Let's actually draw out that job too. So there's going to be let's call it an ingestion job. We'll talk a little bit about this ingestion job in a second here, but it'll look something like this. So this is going to be kind of the high level. We'll talk about what this is in a second, in this like storage layer. But that's kind of like going to be the high level here. And so there's more that could be done here, but we're gonna skip some of those details and come back to this ingestion here. And so that's kind of how this structure would work. There is a world in which, in some places, they would actually have something like a Kafka library in here directly, and they'll kind of avoid the need for an API to go directly to your streaming layer. That's an option. I haven't seen that as frequently done. There are a few companies I've heard of that do this, but that is also a possible option. So in this world, what happens is that this data is actually very trusted. This is trusted data because you own these, you as in your company owns these microservices. And so this is considered trusted data. And then your next one, if we're going to go down this like trajectory of kind of like normal classic ecosystems, is going to be your client data. And so a concrete example of this would be things like your an app, things like that. This is data that's produced. This is data that's generally not produced by you. So you don't control it, and it can be essentially faked or things like that. It could be faked. It's going to be an app. It's going to be, a game client. It's going to be things like that. Now, this data likely also ends up at a collector, although likely some sort of public-facing collector and some sort of private-facing collector when it comes to, the overall architecture of it. And so this data will go to your public-facing collector, and then that data will likely get fed to your private collector. So something like this. The reason why this Kafka architecture isn't as common is because this exists, and you're not going to have some sort of Kafka connection directly in your clients, obviously. And so you still need something like a collector, publicly. And if you need a collector publicly, you might as well have one privately. So generally, that's why this is a less common approach. So it's probably going to be something like that. Actually, in this world, it's very possible for the users to kind of mine the address that's being used here, and then they can send fake data to you. And so in that world, this data is not trusted, which means you have to treat this data very much like it's you got to treat this data carefully. You got to take it in aggregate. We're going to talk a little bit more in a second here about how some of this data gets through. We're going to complicate the picture, but we'll keep it simple for now. Okay, so that's kind of how that works. There's a lot more details about how some of these might work in other domains, like how would you deal with this if you were a game. There's some complications about how that works. How would you deal with this if you had different kinds of architectures that aren't microservices? For now, we're going to leave that alone because these are the two most common ones, and we're going to move on to other areas. Well, actually, I will mention a few more things actually, since it's important. So there are also a few things here that can happen, and so an example of something that might happen is so this here is going to be something called event-based data. So this here is event-based data, and this here is client data. Let's say when we're talking about an event-based data, the implication of that is that a single business event occurred. So maybe a sale happened, maybe somebody moved something in your application, just like kind of things like that. And so that's how this data gets collected, and it's going to be sent primarily through your code. There are other things. There are other kinds of data. We'll call this dimensional data. And in dimensional data, it's not exactly like that. Another word for this is slow-moving dimensions, things like that. These are going to be things like users tables or things like that are like kind of updating slowly over time. What's another example of this? It could be things like player data. We'll use a table. That's the simplest example. And the way that these are normally captured is, so whenever you got a microservice, likely you've got a RDS, a SQL style table over here that's kind of capturing this information. That's how this architecture normally works. You're going to have a SQL style data capturing this data. We'll go with the users table example. And what will happen here is you're almost certainly going to need something that's scraping this data. Some sort of job that's scraper, let's call it, that's going to scrape this data every so often. So scrape every so often. Now, when this happens, there's a variety of options for what you could do here. You could send this data directly to your collector. Actually, it's more common in this world to potentially send it directly to your storage layer. So there are really kind of two options here in terms of how you might collect this data. But so you're going to scrape this data every so often, and then you're going to send that data over and store it. That's kind of how this works. Another option instead of scraping is actually to do it's to pull the data directly through transaction logs. And so every SQL is going to have some sort of transaction log system. And then in that world, you would send that data directly to your collector. And so I'll just move this one here. So those are your two options in terms of how this works. This would be the kind of the new way of doing things. So this is like bin SQL logs, replication, things like that. That are coming through your SQL. And so like, let's say a user changes their email or something, you get one transaction here, which sends that to your collector, which then gets collected. This option is more complex though, because it's a slowly changing dimension. So you're going to have to deal with that in the downstream, which we haven't talked about yet. This one is simpler and it's safer also. And so there is a world in which you might have both of these actually. And so that's kind of like this dimensional data sets. And so I think the only other one that I'll mention is actually potentially external data sets, like data sets you don't control, even outside of client data. These are things like analytical data or data you're getting from other companies that isn't like your sourced data. So we'll go ahead and call that like non-source data or like other data. And in this world, there's going to be likely some sort of integrator that you're going to use that'll pull from maybe somebody else's API, some sort of like non-other API. an integrator that'll take this data and then submit it. And then it actually, in this world, you'll also very likely pull that data into your storage layer directly instead of kind of going through this collecting system here. So that's kind of like this system here. And we'll call that other data. So that's kind of like some of the examples. There are, again, potentially infinite examples of how this collection might work. Before we kind of move into this storage layer, the one thing that I want to talk about is exactly how this data is getting collected. Right now, I haven't really mentioned that or talked about that. And so let's go ahead and do that. It's not often, I would say that maybe 50% of the time a company will have this, but you will want, likely, a schema registry to register the schemas of all of this data. And so when it comes to a schema registry, in terms of the architecture, it will kind of sit in the middle here. The collectors will talk to it. And the way that the schema registries work is that the user, when they're developing their code in whatever language, will have an IDL. So let's call this an IDL, and you can choose any format you want here. And so it could be protobuf, it could be JSON schema, it could be Avro, whatever kind of IDL you want to choose here. And then this is going to define the data and what's in it. So that's what this IDL is for. And so let's say that you were writing some, it's Python code or Java code or whatever. You will have this IDL alongside your code, which will compile into DTOs, let's call them, data transfer objects, or DAOs, whatever you want to call them. It'll compile it into classes. That's the better word, into classes, into this code. And these IDLs are registered and pulled from the schema registry. So that's how this system here works. So this is we'll call this defining schemas. And so this is an important step because you're going to want your schemas. The other thing that the schema registry does is it does version control, and it'll manage, and this is really the most important part, it's going to manage schema evolution. And so that's going to be, are you forwards, backwards compatible? A lot of the times you'll actually choose at the schema registry layer which ones you want to be forwards or backwards compatible. You'll be strict about it sometimes. You'll be like, oh, actually, we're only going to allow forwards or backwards compatible. It depends a lot on how your things work down here. Likely, you're just going to want additions and you're not going to want deletions. That's the primary thing that you're going to want to restrict, which means you'll want to be forwards compatible in this case. And so you'll register these schemas through this structure here. And that's kind of how this works. Once you do it this way, the one thing to mention about this is that these schema registries, if you've got a mono repo, this is kind of easier. You can just have a single one. If you have a sort of a distributed repo structure in your company, you're going to probably want a distributed schema registry. But either way, the registering to and from this schema can get tricky. Because it might need to be involved in build pipelines, and then you need, every repo needs access, all development environments need access. So, it can get tricky in this structure. I'm not going to go into much more detail than that about how this works, but there's an entire, organizations that could work towards this structure here. Okay, so you've got that schema registry, and then what'll happen is that once this data is coming in, it's actually being validated against the schema registry. Your data is being validated. And then likely what'll happen is, if we take this a step further, is if your data is good or bad, you're actually going to have potentially two options. You're going to have your good topic, and then you're going to have your DLQ topic. And depending on the validation, it might offshoot onto here. And we're going to delete this to simplify. architecture here, the diagram here. So it might go here if it's bad. So if bad, it'll come here. If it doesn't pass validation, it'll come here. If good, it'll come here. So that's kind of like a way of doing this. And then, there's like whole, like how to deal with this. There's entire structures on that. Like it probably still gets stored, but in terms of how, there's a lot of options. But that's kind of like how this ingestion layer works and how it'll eventually get to your streaming layer here. The one thing I'll mention on top of that about this is there's paradigms for how you might do Kafka, and like Kafka topic and cluster design is its own entire ordeal. And so you might have, for example, like a single fire hose topic. I've done that before in companies. You might actually have topic per schema. That might be an option. And then even on top of all that, you might have like Kafka clusters per like, some sort of logical grouping. Like maybe you'll have, a Kafka cluster for your microservices, or maybe even sharded by something. But there's a lot in terms of like how this is designed that I'm not going to go into right now. I'm just kind of simplifying that part. Okay, so let's talk about this storage layer. And so what is your storage layer here? In almost all respects, your storage layer is going to be some form of distributed file system. I think it's worth an addendum here to talk about distributed file systems. I always like to use a kind of Triforce as an example here about how distributed file systems work, because it's a rather important topic, because kind of every data ecosystem in the world uses it. So this kind of like distributed file system, and in general this whole structure of how this is going to work, boils down to a few things. So you're going to have your distributed file system. That's going to be your first thing. And so this is a file system that allows, essentially, imagine it like you have your normal file system. You've got copy and move commands you could do, whether you're Windows, whether you're in a Linux-based organization, right? You've got your copy and your moves. What a distributed file system does is it basically was like, hey, what if we take a bunch of these, cheap spinning disk style storage, we put them all together, we combine them together, and then when somebody does a copy or a move command, we'll actually be like, okay, which disk is this from, right? And then you take this concept and you scale it up to like a mega mammoth concepts, and that's kind of what a distributed file system is. It's basically keeping your copy and move command structure, but then behind the scenes, instead of a single spinning disk, it's targeting a collection of bajillions in the case of others. So this is like things like S3, and then Google and Azure have their own versions of it. The most common one here is S3. It's a blob storage is another example for this, but that's what these distributed file systems are. So that's kind of like DFS here. And then your next one is actually going to be your execution engine. And so your execution engine is going to be like, okay, so you've got a file system, which is distributed. How do you go and access that file system? How do you say, well, if I wanted to do something, take an action, how do I do it? So in the olden worlds, you would write actual code for this. So you would write, for example, MapReduce code in Java or something like that. In the modern example, it's SQL. It could be PySpark. It could be some sort of SQL-based language here, something like that. But what'll happen is that will get converted into. It's going to get converted into calls to the DFS. And then it'll go call that DFS, and then I'll kind of bring it back to you. And this is like actually a very complicated structure. There's all kinds of like for loops, and there's going to be for loops involved behind the scenes. It's like a whole. It's basically a giant compiler style system here that's doing translations into different languages and stuff. This is a rather complicated system, but that's what the execution engine is. There's again a lot of options for these. Spark is the most common one nowadays for this. Actually, this execution engine can get more complex than that because I'm talking about batch systems here, but you could talk about streaming systems, which are their own execution engines, but we'll keep it simple and we'll say that this is Spark in this case for a batch system. So you've got your file system, you've got your execution engine, and then you've got your query language. And so this one here, we talked about it a little bit down here, but it could be raw code, it could be SQL, it could be all kinds of things. And so your query language is really a choice. And actually, technically, you could make your own. You could just make your own, new language here. Insert language, and you get your, you get your language, and then that language is just how you're interfacing with this translation layer, so that you can then go find the files that you want. And there's just a lot of languages out there, and this one is by far the most common. So there's like PySpark, there's Spark SQL, there's pure, there's Java versions of it, there's Scala versions of it. There's all kinds of languages you can use, and you can build your own and everything like that. And these query languages will change depending on what you are doing here with your Spark, all that stuff. And then the other one that's common to talk about, but I think it's probably the most important, or one of the most important one, is the metastore, which I like to put in the middle because it kind of houses everything. And so what the metastore is kind of its own, it's going to be its own, probably some sort of SQL database, but it can be a lot of other things. It could be blob storage too. It could be a lot of other things. In modern ones, a lot of the times you'll reuse the DFS for this, but what it is essentially a set of schemas to manage your entire data ecosystem. And so it'll be like, okay, so you want to reach your DFS, right? You want to go reach it. But the question is, where is it? And so that's what this is doing. So it's like, where in the file, in the DFS, is my data? That's an example. Another really important thing that it does is it's what schema is the data in. That's another example. There's a lot of like other complex things that this, metastore does, but that is the short and skinny of it, is that it's managing these types of information. You're going to see kind of an example of all this in a second here, but that's kind of like the trifecta of how this works. This was originally kind of in like the Hive ecosystem. That's how all of this was originally created. So you had like the Hive metastore, you had the Hive execution engine, you had HDFS was the original version of this, and then you had kind of like the Hive QL for this side, and then you had Hive here. So that's kind of like the original structure of this, and then you had the Hive metastore, of course. And then it kind of expanded from there into a lot of other things. But the core of it still remains. A lot of the times, if you go inside like a execution engine or an ecosystem like this into its depths, you'll still see a lot of the word Hive in there. It's just a little history lesson, I guess. But that's kind of the whole system in terms of how this works. And that's like a useful aside to show you how all this works. So really, all of this so far has really just been ingesting into it. We haven't even gotten to all this yet. We're just at the beginning here, which is the distributed file system. We're going to go ahead and say that this is S3 in our example. Now, the reason why this is important here is that how you store it is everything. And so you can't just like store the data willy-nilly in your file system. Otherwise, you're like, where is the stuff in the file system? It's going to be impossible to know. It's going to be hard to query. There's a lot of things. And so really what ends up happening is you need a partitioning scheme. This partitioning scheme is everything. It's king. And what that looks like is likely S3:// or, if you wanted to say, if you were in the old school, it would be like HDFS://. And so this is like you're accessing your file system. Locally, you do this too. It's C:/ or things like that. So that this is like actually very similar to a local file system. But you're going to have that. And then what you're going to start doing is you're just going to organize the data. A very common option is something like date. Obviously, the first one is always going to be the table name or schema name. And then you're going to have date, let's say. Maybe you can do hour in there if you wanted to. Another option that people do is they'll do like region. We did that a lot in my previous companies, as you would have region, and then you'll have like file dot something. We'll talk about that in a second. But that's kind of like how the structure works. And then let me show you really quick how the Hive metastore plays a role in all of this. But let's say that you were doing a query language, and let's say your query language was SQL-like. And so you were going to do select star, let's say, or let's just do select, let's just do select star from table A, right? And then you're going to do where region equals, whatever you want, North America. And then you're going to, and date equals, 2025 or, 12, whatever we are at, 12 today. Something like this, right? And so what ends up happening is you can see exactly how this works. So this table is going to filter immediately. So imagine without this, you don't really know where things are. With this, the metastore stores where this information is. So it knows immediately, oh, actually, I know where table A is. So instead of querying my entire 5 petabyte data and iterating it all and trying to find where this data is, the metastore is telling you, oh, this table is right here. I just go one level deeper into my distributed file system. And then it's like, okay, what about from there? Oh, the region is there, and then the date is there. All of a sudden, you filtered it down and you have an exact query for the files that you need. So there's obviously some complications in terms of how the DFS actually stores its data, but we're not going to get into that. This is called a partitioning scheme. And it's the thing you need to decide when you're creating a data ecosystem, how you want to do your partitioning. It's likely something like this, though. It's probably going to be nothing much than that. Maybe you don't need region if you don't have that concept. But that's kind of like the structure for it. So that's kind of a partitioning scheme. You're going to apply this to every distributed file system you work with. Obviously, some companies provide kind of a lot of these in the box, so you don't need to think about this a lot. But if we're talking about from the ground up how this architecture works, this is how it is. In terms of the file, this one here, this ... the file type. So this is also important. Obviously, you could just do like CSV, but like that is not ideal for this type of architecture because what we're building here is a data layer. It's a data ecosystem. What you want to do is aggregate queries over potentially, terabytes, gigabytes of data. If you weren't dealing with that scale of data, you don't need any of this. This is for when you're dealing with years upon years of data that's scaling into the terabytes, into the petabytes range. And so if you're doing that, it's not CSV. Okay, so generally with the file type, you have 2 options. You've got row-based and you've got columnar-based. I'm not going to talk about how these two are different in terms of like how these two work, I should say. Row-based is going to be able to let you pinpoint a single row. That's the benefit of the row-based. And then in a columnar-based, it lets you pull out an entire column quickly and efficiently. So that's the differences between these two styles. In a distributed file system where your whole job is to do querying of aggregate, like you're going to do sums, you're going to do like, like other things like that. You don't want a row-based system. You want a columnar-based system. And for that, the king is obviously Parquet as the file system. So that's a columnar-based one. CSV is a row-based system. There are other that are in this step. In the past, there was others, columnar-based file formats. I think ORC maybe is still around. That used to be a thing that was potentially in contention, but not anymore really. But that's what this is. And so when you're writing this out, you're definitely going to want it to be a Parquet file, basically. And likely also won't be one. It'll be probably multiple files. So that's kind of how this works. In terms of your ingestion job, there are a lot of ways to do this. And so one option is, let's say every 15 minutes, batch your jobs, and then write out a single file. If you do it this way, for example, I've done this in the past, obviously that means you won't get your data until after 15 minutes of point of ingestion. But in a lot of situations, this is fine. You don't need anything quicker than that. If we're starting to get into the real-time world, a lot of things change, and I'm not going to get into that in this architecture. But so that's if you're going, that's an option, for example. There are other options. There are also architectures that, so if you did it this way, for example, you're going to write 4 files per hour, essentially. And that's actually a reasonable amount. So you can that's actually a very good, generally speaking, file distribution, because your files do matter. Like the size of it matters. You don't want them too big. You don't want them too small. Files not too big, not too small. And so that's for that reason, you're definitely going to want to do some sort of structure here for this. There are other architectures that are more common nowadays where you're just like constantly streaming data into your distributed file system. And then there are jobs that are compacting your files. So this is like, there's Delta, Databricks' Delta does this, but I'm sure that there are plenty of other examples of this out there that do this kind of structure. The issue with this approach is that the first, hour chunk, the latest, I should clarify, the latest hour chunk, querying is going to be slow, simply because lots of small files. So I'll clarify that the small file size problem is a real thing. And so in general, this means if you have too many small files, queries slow to crawl. So that's why you need files not too big, not too small, specifically for this. So that's kind of the structure here in terms of how this works and how the ingestions might work. The only thing that I'll add to this before I move on to processing and visualization is, I haven't mentioned this because I haven't been in many places that do this, but there is a value in such a thing as data registry, into a data registry. So a data registry, the idea behind this is that similar to the schema registry, where you're registering a schema, a data registry is a layer above that, and that's where you're registering the fact that your data exists at all, what that data is, and in a lot of ways, what data sinks that data should go to. This is very much an organizational play here, and likely lands its own structure here. So you can't send your data unless you're registered through the data registry. And then when you do that, you're going to register like who you are, who are you, what's your ownership, what's your like email name, and then you'll have SLOs or SLAs for this data, et cetera, et cetera. It also, registers, it registers syncs and even potentially mappings for those syncs. So that's an example of something that this data registry can own. And the reason why that would be important is, so far I've mentioned storing this data in S3, in your distributed file system, which is probably your main one, but that might not be the only one. You might have other syncs here that you want to store to. So this could be, other syncs. So you might want to store it in some sort of, graph-based data, and maybe not all of your data. I mean, you probably want all of your data stored in your distributed file system, but some of that data you might want in other formats. You might want graphs. You might want, some sort of NoSQL. Who knows? There's all kinds of potential options here. And for that, your data registry is important and valuable because you can schedule your mappings for it. And so mappings being from schema to a storage layer format mapping. So schema to storage layer mapping. So that's a valuable thing to show here. And you can be like, hey, some of this data, then this is where the data registry it could be a layer here. So let's do something like this. Some of the data might end up going in some places and some of it might go in others. And then the data registry would be the one that can route all of this with its metadata. So that's another example of something that would fit into this architecture. Okay, and then that's kind of like the storage layer. Let's move on here to the processing layer or execution layer. Okay, and so once you got all this data stored, you need to manage that data. What we like to do is we like to call kind of like where we're at right now as like a raw layer. So your data is very raw. It just got into here. It hasn't even been deduped. It's not been potentially cleaned up. And so this is your kind of raw layer of data. And so we're going to need to clean it up. And so the way to do that is, generally speaking, you're going to have a data ecosystem that's structured with an execution engine and a scheduler. And so let's talk about that, as well as a developer environment. So let's go ahead and say execution engine. And then you're going to have a scheduler, and then likely some form of developer environment. Let's put this down here for a second. So your execution engine, we talked about this. And so in this case, let's say it's Spark. That's a really common execution engine. And then you're gonna have a scheduler, which, in a lot of cases is something like an Airflow. You could have there's so many options for a scheduler. You're not limited at all. The job of a schedule is to schedule jobs and then create a DAG for task-based ordering. And you're going to see why that's important in a second. But you're going to define your ordering and of your jobs based off of this. And then you'll use Spark to do the execution of it. And then you have your developer environment. Now, there are many options for this. I'll give you two. In a lot of places, the main option here is actually some sort of web-based notebook environment. And obviously, if you do this, you need some sort of deployment system for how to deploy these notebooks to the world and things like that. And then another option is a local-based development. There are pros and cons to all kinds of developer environments, but the idea behind these is that you're writing code, which could be SQL, it could be PySpark, and by SQL I mean like Spark SQL in this case, because we're using Spark. It could be Java, Scala SQL or Scala Spark. It's just a lot of options here, right? So you're writing your code, and it's like, where do you write that code? The benefit of this web-based notebook environment is really that it has and when it is web-based like this, they're all pointing at. We'll put this down here real quick. They're all going to be pointing at Spark. There's going to be a Spark cluster involved that's going to manage your memory. And that's really useful because, in this world, you can have an environment where you do a query and store the results in memory for you to then play with. And then you have fancy displays, to see the data, etc. There's just a lot of quality of life things in this web-based notebook environment that a lot of people use. A lot of engineers prefer this, and then a lot of more analysts, data scientists might prefer that. That could be structure. In the local-based environment, you have a lot better, source control. You're going to have better modularity of code, things like that. And so really, it just depends. This one will also connect to some sort of Spark environment to run your code locally, but then you have issues with how you're going to run your local. Your local has to connect to a Spark, whereas in this web-based environment, your web's connected to Spark. And so there's pros and cons to both of these architectures, but you do need to choose how your developer environment is going to be. It's a choice you have to make. And then, of course, your scheduler is likely local-based, and then it'll be like a GitHub repo or something that has all this information in it. Okay, and so that's kind of how this system will work. In terms of what this is doing, who's writing code and what are you writing? You're not going to just write whatever. There's going to have to be some sort of structure to keep your data ecosystem kind of clean. And so every company is going to have their own way of doing it. I will give you a system that I've used in the past, but these can get as complex as your company is. You could have so many different layers. And so an example of something that we've done in the past I've done in the past is you would start with a single layer. And so you start limiting people's ability to really play with this data so that it doesn't get too messy. And so you're going to have a raw layer to a clean layer. And so in this world, all you're doing is basic cleaning. You might do dedupes. You might have certain mappings or maybe renamings done here. And this is useful for in the future world where data starts drifting or data starts versioning and changing. You might need a layer for this. So I think keeping this as a layer is a rather valuable layer. And then you have basically a structure that's layer 1 all the way to layer n. So something like this. And you're going to see where the DAG comes in here because each of these is going to be a layer. So what'll happen is, let's say you've got table 1. And then you've got table 2. So you might, for example, join these two in some sort of aggregate in order to simplify some things. And that'll produce a table 3, let's say here, right? And then let's say down here you've got table 4. You might then be like, okay, well, actually, I need this raw thing combined with this thing to produce a table 5. Okay, and so now you're seeing this is a DAG structure, and that's what Airflow is for. So Airflow is managing this task-based ordering of these jobs. And in almost all cases, it's scheduling these jobs in some sort of like daily or hourly fashion. There is a world where some people would say, actually, this entire thing should be replaced by some sort of streaming version of this so that you're doing joins and stuff in streaming. I don't think we're there yet. I don't think that type of architecture where your entire architecture is done like that, it's just too expensive. There's just no need for that. This is going to be significantly more cost effective. And so while you will still have situations where you might need to do joins and these types of things in your streaming layer for extraordinarily quick tasks, and so I think fintech would be a perfect example where stuff like this is probably happening. In most companies, you're going to want the majority of your petabytes of data being managed and processed through this structure. It's cheaper, it's faster, things like that. And then it'll go all the way to layer N. And so you're gonna want to do something like this. All of these should actually be connected with your schema registry, so that you're keeping track of all reads and writes to it. You're keeping track of all of this stuff in order to get lineage out of this. So at the end of the day, you're like, hey, if I've got a table, what are the sequence of tables that produce this? And so that's why you're going to want to do this, and that would involve potentially creating libraries here. So we'll call this, we'll say libraries to manage this type of creation. There are actually plenty of open source libraries that do this, so you have choices in this space. You can also build your own. It's not too complex in this case. In a lot of cases, you actually might want to create your own because who knows what your schema registry looks like. There are options for this, by the way, which I didn't mention. The common one is the Kafka schema registry. You can also spin up your own. It's not too complex to do this. You just have to have this like compatibility check. Who knows? And so that's why in this case, it's very likely that this library will be actually custom, just because your schema registry might be different, your structure might be different. You might want different rules for your layering systems. But this is important because there could be a world where you might end up having like a swamp where people are producing things they don't know where it came from originally. They have no discovery of these things, and bad things can happen. So as an example, I remember in the past there was a situation where there was a very important table at the end of the line. And when nobody knew how this table was created anymore. It had been created and structured over the course of many years. And eventually there was something like 60 layers deep nested DAGs that produced it. And that's bad. You just don't want a situation like that to exist or occur in your ecosystem. And I imagine this is rather common in a lot of data ecosystems. And so for that, you're going to want you're going to want to be able to keep this clean and managed and look good. Now, the one thing I'll mention in the Exia AI here is that all of this presupposes you've got people doing this work. And that's like, maybe they're data engineers. That's what I'm used to. Maybe they're the data analysts. Maybe they're data scientists. There's a lot of terms for this, but there's people doing this work. In the Exia AI, there are plenty of companies out there that are likely trying to simplify this. But let's ignore that for a second. I'm going to go ahead and give you 3 options for how this works. So you can have people doing this work. And so that's like this. You can also have, the better way to put this is dedicated people doing this work. The problem with this approach is that you're going to have a bottleneck of these people. And so this is an organization problem now. It's like, how do you hire these people? Should you hire a lot of them? Should you not? And so the issue with this is that your supply is constrained, is independent of your demand. And so let's say that you're producing a lot of features, a lot of things are happening. If you don't increase the supply of your dedicated people, your entire ecosystem will fall behind because there's things being made that these people can't track. And so you do have a disconnect in this world, and that can be very painful. And a lot of companies have issues with this, mines included, the ones that I've worked at. And so another world where you're doing this is you kind of have like a split world, split work, where you've got some sort of a UI, UX, that helps people write this. And so you can manage all this via UX UI. and then you can give people the ability. So instead of having to write, the SQL, you can have like a UI that kind of abstracts away that there's airflow behind the scenes and all of that. And then this allows you to say, hey, any team, anyone can write this. We used to have this. We actually got rid of it to clean things up in the past, in a past company that I worked at. So you can do this. The issue with this is that very likely you will end up with a swamp if not managed. And so in that world, a lot of companies, what they'll do is they'll actually then have some dedicated people, and their job is to manage other people's code, give advice, tell people to get rid of stuff. That they're basically managers of the ecosystem. They're like curators. Actually, a better way to put this is they're curators. So that's kind of another option for this. And then, of course, in the age of AI, some people are like, hey, this seems like a great place to potentially play here. And maybe you can have, can you have AI curators? Can you have maybe AI just help make the SQL? There's a lot of potential places to play here, but it's not an area I'm going to dive into really here. And so that's kind of this processing structure. And so what you end up with here is, I'll call this this is your data ecosystem here. And so you can do a lot of cool things here. So for example, you could be like, this is locked, for example. No access. Nobody can access this. This whole thing, maybe nobody can access it, and you can only access it from here on. And maybe you can start organizing these into schema. Organize these into schemas, structures, schema structures, and groupings. There's just a lot of things that you can do in the space. But at the end of this, what you have is really an ecosystem of tables that you can play with. You can either use them for training data, or you can use them for analytics. There's a lot of interesting conversations about the different types of table structures that might result in that. And so you actually might have a split between, potentially, feature style tables and then, analytics style tables, that are used for creating reports versus, training models. And there are companies that are in this space that kind of deal with a lot of this stuff. That's the short and sweet of this. And so that's all happening essentially in your distributed file system, remember. And then we talked about execution, metastore, and query language. And so that's kind of everything here. And then kind of the last layer I'll go over quickly here is your visualization layer. And so there are many options here, but essentially the goal here is really just to visualize any reports you have. And so this one, you could just use Tableau. You can use Looker. There are some open source versions of this, but the idea is that they query your tables probably per day or 30 days or, a week or whatever. And then they're going to create visualizations for it. So they'll create charts, line goes up type of charts. So it'll be like line goes up, this type of thing. That's like the point of it. There isn't really much to say here. There are, of course, other visualization tools depending on different, syncs you have, which we didn't really get into. This is all in your ecosystem layer. But that's kind of how that works. This is all generally focused more exclusively on your kind of reporting structures. There's an entire split that's going to happen here in terms of how you start dealing with models, with training, data for training, data for modeling. I'm not going to go over that in this example. I think this was already more than enough data more than enough information for one example, for one session. But I might do a second session that kind of goes over in more detail how this type of structure might change to accommodate training models in a consistent fashion, deploying those models, and the many methods in which you can deploy those models. That becomes more of like an AI layer discussion, but it has everything to do with this structure, because this entire flow from start to end affects that, especially because all this is data. If your AI is supervised learning, especially, or primarily, this whole flow will affect it. And so, but this is, I think, a pretty good 101 introduction into this ecosystem, to how this works. Thank you very much for coming all the way to the end and hearing all this with me. I hope this was helpful for somebody out there and in learning this architecture and how data layers work. Thank you very much. Again, my name is Serj Kazar, here with Exia Labs. Thank you.